As we now shift gears to talk about forces, the first thing we need to understand is how this unit is going to be different from our last unit. So our last unit was kinematics, which was the study of how things are moving. The study of forces, which is also called dynamics, is trying to study why those things move in the first place. And specifically in our course, we're going to study a lot of Isaac Newton's model. And Isaac Newton was one of the first people to talk about an idea of forces as something that could relate to motion. And so we still follow Newton's basic principles that objects move because a force has been applied to them. But specifically when that force is applied, it's not just that the object will move, but a force being applied can make an object accelerate. And there's a key difference there, because an object that's moving didn't need a force to make it move. It might have already been in motion. But if it accelerates in any way, if it speeds up or slows down or suddenly comes to a complete stop, that can only happen because a force was applied to them in some way. That's what Newton's basic principles say. So in our course, we're eventually going to talk about common forces, things that we deal with in our everyday lives that we've given names of forces to. But all of the common forces that we deal with in our everyday lives, at a much smaller level, are what we call the fundamental forces. So common forces are really just fundamental forces acting on a larger everyday scale. But at the more microscopic or particle level, there are really only 4 basic forces in nature. And in fact, when you're studying at higher levels of physics, we tend to not even call them forces anymore. They call them the 4 basic interactions that nature goes through. And this chart is arranged by the strongest force at the top down to the weakest force at the bottom. But I'm actually going to go through this chart in reverse order. I'm going to start at the bottom. And so the one definition you already have there on your page at the bottom is something that's an attractive force exerted by any mass. Well, we call that gravity. That's something we've already talked a little bit about in this course. Gravity is an attractive force that is exerted by any mass. And so a simple situation we could map out is, for example, if we had a beautifully drawn sun and an even more beautifully drawn Earth. That's good enough for the Earth. The idea with gravity is that it's a mutually attractive force. So anything that has a lot of mass, like the sun, will be attracted to the Earth through what we call the force of gravity. And we often write that as F with a little subscript G, Fg, the force of gravity. But at the same time, the Earth has mass, and it's going to feel an attractive force towards the sun. And that's how we are able to stay in orbit around the sun. We feel a mutual gravitational attraction between ourselves and the sun. And while gravity is one of the fundamental forces, it's also one of the common forces that we're going to deal with a lot in this course. One of the ones that's not a common force that we'll deal with much in this course, but it's still useful to talk about it, is the next one up on the chart. It's called the weak nuclear force. And it's called the weak nuclear force, but the weak part just means that it's weaker than another force we're going to talk about later called the strong nuclear force. But the force itself is actually not very weak at all. In fact, it's very strong. And that's what the numbers in this column are trying to indicate for you. So if gravity has a relative strength of 1, we're saying that the weak nuclear force has a relative strength of 10 to the 25. What I mean by that is the weak nuclear force is 10 to the 25 times more powerful or stronger than gravity. So if you think about how strong gravity can be, and it's strong enough to hold planets in orbit, as we just talked about, the weak nuclear force is 10 to the 25 times stronger than that. So it's an incredibly strong force. But what does it actually do? Well, there's some tricky details behind it, and we won't get into a lot of what the weak nuclear force really does, but the key final result is that it can turn neutrons to protons. And that's a pretty fancy trick. That's not something that you can do with a simple chemical reaction. That requires a nuclear reaction to occur. Specifically, when a nuclear reaction occurs, we call that some sort of radioactivity. And this force is the one responsible for radioactive decay. So that decay process works in the following way. For example, if I have a certain nucleus that has, let's say, a certain number of protons and neutrons. So I'm just going to draw 7 little circles here. And that is representing my nucleus. Those are all protons and neutrons combined together. And to label the protons, I'm just going to put some plus signs on them. So here I have, let's say, 3 protons. Oopsie. 3 protons all connected together there. Well, this weak nuclear force is responsible and helps guide us through this radioactive decay process. And eventually, after that decay process has occurred, we still have 7 particles in the nucleus. So I'll draw 7 little circles again. But what we find now is that what was 3 protons and 4 neutrons is now 4 protons. And the neutrons are filling in the gaps in between. And when this happens, it's not just a strict one-for-one transition. There's lots of other particles and energy released in the process because there are different amounts of energy associated with protons and neutrons. And so when this change happens, we also see some other stuff, what we call radiation, coming out. And there's actually 3 different kinds of radiation, what we call alpha, beta, and gamma radiation. Those are all just Greek letters. Alpha and beta radiation are actual particles that are shot out, and we'll talk more about this in our nuclear unit. And gamma radiation is just a form of electromagnetic radiation. So it's kind of like very high-powered X-rays that are extra damaging and dangerous to you. So we have to be very careful of radioactivity, but it can also provide us with lots of energy. Looking now just one up the chart, we have something that's a result of moving charges and interacting fields. Well, specifically we call that the electromagnetic force. And always try and spell it right. So it is the electromagnetic force. And if we look at relative strength again, we see that it's 10 to the 36. So again, if we compare that back to gravity, that means the electromagnetic force is 10 to the 36 times stronger than gravity. So it's an incredibly powerful force. And that's why particles are able to connect together into more complex molecules, because the electromagnetic forces that hold protons and electrons together help to build objects and build larger, more complicated molecules. And so specifically, when we see maybe 2 charges that are interacting, so if we have a positive charge and a negatively charged object, well, you know from your basic understanding of electricity that those will attract one another. So there is an attractive force there. If we had maybe 2 of the same charges, like 2 positively charged particles, they would repel one another. Like charges like to push away and feel a repulsion. But it's not just moving charges, it's also interacting fields. And one kind of field is a magnetic field. That's the kind of force field that's produced by a magnetic object. So if I took a bar magnet with its north pole facing another bar magnet that has its south pole in that direction, you might have heard this before, and we'll talk more about this in our electromagnetism unit, that once again they will feel an attractive force, just like opposite charges are attracted, opposite poles of a magnet are attractive as well. And all of that is a result of the electromagnetic force. So you can maybe just remind yourself and put a little note that it can be attractive or repulsive. The last one at the top of our chart is the strong nuclear force that I mentioned earlier. That's the strongest one that we know in all of nature. And again, that explains why the other nuclear force is called the weak nuclear force. It's not because the weak nuclear force is actually weak, it's just weaker than the strong nuclear force. And we can see that when we look at its strength. It's 10 to the 38 now. And so that's 10 to the power of 38 times stronger than gravity. And we can also see that it's stronger than the other two clearly because the power of 10 is not quite as big. So what does this force actually do? Well, it's the force that keeps the protons in the nucleus. So why does that matter? Why does it need to hold them together? Well, picture what's going on in a nucleus. So once again, similar to what I drew down below, I just draw some circles again to represent a nucleus. Those are just a bunch of protons and neutrons. Well, some of them are going to be protons. And then there will be some neutrons in between. The neutrons have no charge at all, but we just talked about how like charges repel one another. That's what the electromagnetic force is trying to do. So on the one hand, there's an electromagnetic force that is pushing all of these charges away from one another. So trying to push and separate that nucleus. But we know that there are lots of stable nuclei, lots of nuclei that hold together. And they do hold together because there must be some stronger force that pulls them back in. And so that green force that's pulling them all back in and holding the nucleus together is what we call the strong nuclear force. And so one thing we can take from that is that the force represented by the strong nuclear force specifically must be greater than the electromagnetic force. And we can see that that must be the case because nuclei are typically stable. They are held together despite the fact that electromagnetic forces are trying to pull them apart. And we need that strong nuclear force to do that. In class, we're going to watch a few videos that can hopefully summarize these things a little bit better. And I'll talk about what the chart at the bottom of the page is trying to indicate as well. In the long run, though, I'll just say these four fundamental forces are what we actually see at the microscopic or particle level is going on, but they're not so handy all the time in terms of solving problems in our everyday lives. So we're going to move on from here in our next note to talk just about some more common forces that we will see in our everyday lives, but we'll talk a little bit in class about how those are really just bigger versions of some of these fundamental forces that we talked about in this note.